Yeah, thank you for letting me speak. It's been a fun week. I'm still here next week. And today I'll tell you about the Relaxion, mostly geared towards what Anson and I did last summer on a new mechanism to realize the Relaxion. But first, I'll sort of do an overview of the Relaxion too, just so that everyone is up to speed, and that maybe helps generate discussion. Yeah. So what I'll focus on is Relaxion with particle production. But first, let's just see what the Relaxion is and what it's good for. And you'll see that it's good for some things and maybe it doesn't look so good for other things. And it's not really a topic that tells you that there's new physics at the TeV scale, so maybe it seems a little bit outside of the workshop, but it's touching the question which motivates a lot of physics at the TeV scale, so there is a connection there, and that question is the hierarchy problem. And particular solutions to the hierarchy problem. And I think we can classify them roughly in two big groups. One is symmetries, which I think is the largest group. And here is just the idea that you can somehow protect the Higgs mass by enlarging the symmetries of the standard model such that the operator of the Higgs mass is protected. And that's what I think most people are familiar with. And practically, it means that if you have, typically in the standard model, loops of particles tend to push the Higgs mass towards UV values. And if you can enlarge it with symmetries, it means that there are extra states that soften this divergence and make the loop finite, or at least only log divergence. And that tells you that, and the scale at which you cut off this this divergence is where the new states appear, and that's why there's this expectation that there will be new states at the TeV scale. And I think that's a very nice solution. It would definitely make me very happy if we discovered partners at the LHC. I think would sort of be in a sense the most satisfying solution. And then there's another big group which is, I think for a lack of a better name, I'll say that landscape solutions to the hierarchy problem. And those are doing one thing that I think it's reasonable, which is, and very sensitive, which is saying maybe the Higgs mass is not just a parameter in your theory, but you should really think of it as a dynamical variable that can depend on the state at which your theory is. So for example, it can depend on the VAV of other fields, it can depend on which phase you are in the theory, and so depending on exactly which state of the theory you are in, this can change. And then if you have a very, very large number of sort of stationary states, sort of local minima in your energy potential, some of those can have a small Higgs mass. And so by just the law of large numbers. And then the problem is explaining why you would live in one of those and not in one of the majority of the ones in which you have a very large mass. And for that, the traditional explanation is some sort of anthropic explanation. And I think that's how you write it. Which then requires you making some assumptions of how you measure things and how you take probability distributions. And the Relaxion is sort of a new entry in this sort of landscape type solutions, in which you have some sort of dynamical evolution reason, sort of cosmological, maybe in a sense, of why, even though it's only a small number of the stationary states in which you have a small mass, but maybe dynamics sort of pushes you towards one of those minima. Right, and so that's the idea. And to be very precise, let me just briefly tell you the basic model of the Relaxion. And it's relatively simple. It's a technical solution to the hierarchy problem, so there will be many small numbers everywhere, but they're all technically natural. And you include the following feature. So you need to include a field which, as it changes, the Higgs mass changes, and so you include, say that the Higgs mass would be at some cutoff, but you also include some very small coupling to another scalar field, which allows the Higgs mass to change as you change the value of the scalar field. You want this scalar field to have many, many minima, so the way you typically do it is imagine that it's some sort of axion-like particle for most purposes. So it would have some periodic potential, which is generating a lot of minima. And the nice thing is that, well, this potential can be somewhat large because it respects some shift symmetry, so it's not generating a very large potential for phi. But because you included the explicit breaking of this shift symmetry, which you need, because if you was exactly shift symmetric, in all of the minima, the Higgs mass would be exactly the same. You need to include a potential that's also generated by the small shift symmetry breaking. And you can think of this epsilon, which in this parametrization has mass dimension 1, as some spurion of this breaking. And so this potential, you can think of it as it has all terms that you can expand in terms of this epsilon squared, phi squared, and dot, dot, dot. So you sort of you put epsilon phi to some power and then cut off to compensate for the remaining mass dimensions. Now, what you'll want this field to do is say that, okay, in some generic point, the mass is equal to the cutoff, but as this field changes, it can do the tuning, sort of cancel most of the Higgs mass and leave you with a very small value. But for that to be true, you need the field to change by a very large amount. Right, you need some field excursion that's given by the cutoff squared over epsilon. So you'll need field excursions which are much bigger than the cutoff. But as long as in any given process, the typical energies are not much larger than the cutoff, sort of energy exchanges and kinetic energies are not bigger than the cutoff, you're still within a regime that you can trust your effective theory. So even though it seems that, okay, doing field excursions that are big, much larger than the cutoff, but as long as no process really is testing this huge excursion at a given, just a single process, it's okay. It's doing this very slowly, very adiabatically. And because of that, because of the potential being just a very, very small potential, so very flat, it's a very good approximation to always treat V as just a linear potential, because it makes calculations easier. And if you see, when phi has sizes of order lambda squared over epsilon, every single term that you have in the potential has roughly the same order. So yes, as you move phi around, the slope changes a little bit, but it's parametrically given by epsilon lambda squared. That's sort of the typical size of the slope. And then the last thing is that you need this barrier height here to depend somehow on the Higgs value. So this is, so for example, need it to be something, let me now call it some lambda c, and then depends on the Higgs valve to the end. So that's how the phi gets to know that the Higgs mass has become small or large, is through this, the fact that this other potential, which can be much larger than this small shift symmetry breaking one, knows about the Higgs valve in a way. Okay, so now, yeah, so how would that look? How does the total potential for phi look? Right, so the sum of this periodic and the shift symmetry breaking one. If the Higgs valve is 0, this barrier height is 0, which is a very good approximation. And then it's just some flat potential. And then at some point here, some phi star, the Higgs mass crosses 0. The Higgs mass crosses 0, and then some small oscillations start, and you create this minima. And then the idea is that because there's a very clear separation between Higgs mass being positive and negative, if you start off in this region where the Higgs mass is positive, that you're in the unbroken electroweak phase, there's no barrier, and you tend to be pushed towards the regions where the electroweak symmetry is broken. But as long as these barriers are sufficient, sort of kind of large, you'll stop in a minima where the Higgs mass is not that far away from zero. And if I take just the n equals 1 case, which is the easiest one, but I can estimate when does the minima, the first minimum start to appear? They start to appear when the slope of the periodic potential becomes comparable in size to the slope of this shift symmetry breaking potential, which is when epsilon lambda squared becomes roughly of size lambda b to the 4th over f. With if I take this n equals 1, it's lambda cube c Higgs VAV over f. So in this sense, and so it will select values for your theory such that the Higgs VAV comes out being epsilon lambda squared over f over this lambda c cubed, which are a combination of large and small numbers. But because you have freedom of adjusting these numbers, you can make 100 GeV show up as a somewhat natural choice. You have to adjust these parameters to get that, but it's not really the same as fine-tuning in the sense of adjusting two different contributions to cancel out, because here if I change any parameter by a little bit, it only changes the Higgs VAV by a little bit. So it's not, it's sort of, you need some conspiracy between the parameters, but you can say that this conspiracy is what's setting 100 GeV as special. And of course, there's one extra requirement, which is, well, if I start off, well, first you have to assume that starting off to the left of this point is somewhat natural, somewhat generic, which I think it's hard to evaluate, but sounds fine, maybe 50% chance where you start. But if you start out off here, and if you just do an analogy with classical mechanics, you know that, well, when I get here, I have so much kinetic energy that I just zoom through all this minima. So you need also a way of losing energy such that you can really stop in this local minima and not just sort of zoom through the whole thing. And the way most Relaxion models work is that the scanning is happening during inflation, and so Hubble friction slows down the rolling of phi. So you try to remain in this low roll regime throughout this evolution, such that when you encounter the first or the first significant minima where this is sufficiently deep, you stop. So this just sort of, so I like to say that there are two very important ingredients for this construction of Relaxion models, which is the sort of the one that people have worked more on, focused more on, which is one, you need a V-dependent, well, I guess Higgs VAV dependent barrier for this cosine, this periodic potential, and I'm distinguishing the VAV of the Higgs from V because I want to use V for 100 GeV, sort of for really the electroweak scale in our universe. And so this means that typically you need some sort of new strong sector that talks to the Higgs, which actually in principle is a good thing because maybe now we can probe it, but also can be more constraining. So it's a good and a bad feature. And getting the barrier, this lambda c, the part that doesn't depend on the Higgs VAV, to be larger than V is non-trivial. I mean, you can do it, but typically requires introducing new states. Sort of you typically need an extra scalar field. But there have been many models of that, but it requires more module building in order to achieve this. And the fact that you need Hubble friction restricts you that sort of the scan must happen during inflation, because that's when you get significant Hubble friction. And one can show that because you need to be sort of in the regime where you're sort of slow rolling, such that this Hubble friction is effective enough that you'll stop when you find one of those barriers, you need a very large number of E-foldings. You need, so this delta NE is just the number of E-foldings, the minimum number of E-foldings that you need to do the scanning. And this is the cutoff to the fourth over lambda C. And then, and so for example, let's say that you've achieved this, that you've done, yeah, and by the way, you can only do this for n equals 2. You can't really do it for n equals 1, otherwise you're doing Technicolor, which I guess nowadays you probably don't want to do. So the best case scenario, this is lambda squared over v squared. So you see that even if you want to solve as sort of just a small hierarchy problem, you already need 10 to the 4 E-foldings of inflation, which is not theoretically, in principle, a problem, but it just requires your inflation sector. Well, you need to model build a little bit more inflation sector, and maybe gives you a few extra headaches. Yeah.
I think if you put all the 4 pi's and so on, I think you can get something like 1 or 2 orders of magnitude of scanning before you get into the regime where you really need.
Or if you put sort of
large number of E-folds. So I think there is you can relax from something like 10 or maybe even 100 TeV down to the weak scale within an E-fold. I think, for example, in one of the paper by Panik or company, they have some region of parameter space where you don't really need large number of E-folds.
Yeah, I'll be.
In general, it's still true.
High, right? You were saying like a little higher.
I mean, in general, this is true, this relation.
I see.
I think the numerical factors all end up on the
one
side, and then there's a small.
Okay, yeah, I'll be curious to see, just because I mean a lot of people seem to have ignored the fact that you need to still be slow rolling, and then it's easy to sort of not notice that. But I didn't put in 4 pi's, and so maybe if you sort of get maximally helped by 4 pi's, I think maybe you can get. Yeah, it will be good to see. Maybe I can take a look later. Yeah.
So then you is not eternal, or it's okay for
you can still you don't need to go necessarily to an eternally inflating. So I think a lot of the models, at least that we looked back when we were writing the paper last year. At first we thought they would all violate, when we realized this bound, that they would all violate eternal inflation, this sort of generic things from, I guess, information theory bounds, but they all sort of passed because, I guess they all passed. They barely passed, but they all passed the test. It was fine. I think it was because their cutoff. Yeah, their cutoff was the test also depends on cutoff and Hubble and things like that, and their cutoff was sufficiently high that it offset part of the problem. Okay, so yeah, I think the nicest feature of this particle production that I'll tell you about now is that it changes both of these things, and so in principle it offers the chance of solving some of the problems. It will come with its own set of problems, but it's separate from those, and so it gives you a lot more freedom. It's like a new tool in your model building box. So since it's Friday, let's do some relaxing with particle production instead of beer. And the idea is, the zeroth order idea is very simple. It's just that, well, we know phi needs to evolve, so it has time dependence. We also know that if you have time-dependent fields, you can excite quanta of different light fields that talk to this classical field that's evolving, right? I mean, you know that from E&M. If you have a current and the current is oscillating, you create a bunch of photons. And because you're creating particles, it needs to extract energy from the source. So the idea here is to use the relaxion as some sort of source of some light fields. And the logic of why this will help with with Relaxion, with the tuning to the small Higgs valve, is that if you imagine a scenario in which in the beginning of the scanning, the Higgs valve, the Higgs had a very large mass, but it was negative, so that it had a very large valve. All particles are heavy, and so you can't really excite any of those modes. And only when you've sort of scanned sufficiently the Higgs mass that you've canceled most of its contributions, so that now all particles are very light, you can start to excite those modes. And as you excite those modes, you lose energy from the relaxon, it can fall into a minima. So it's sort of, you turn on a new friction mechanism because it's some energy loss, and then you can get trapped. So that's sort of the basic idea. And just to make the actual mechanism of how you produce particles very explicit, let me start with a slightly simpler version, which is how you, just Relaxion Higgs abelian theory. I guess it's abelian Higgs, not Higgs abelian. Well, it's so the idea is now you still have something that scans the Higgs mass. Now it will have the nice feature that it's the n equals 0 case of this scenario, so you don't really need the barriers to depend on the Higgs mass. And the one ingredient that you need is you need a U1 gauge field. With this FF tilde coupling that is sort of somewhat generic for axion-like particles. The one thing that I particularly don't find so nice is that the decay constant for this cosine needs to be different than this, such that this coupling is sufficiently strong. So this F prime typically is a little bit big, and if you want this to be efficient, you need a hierarchy between those two. Luckily for relaxons, people had already come up with module building techniques to achieve this two separation of decay constant scales, so I'll not worry about that. But there are people here that, yeah, but once you're doing something like the clockwork, you have a bunch of sites, you can just use all of them. Yeah.
This field also can't be the QCD axion.
It cannot be the QCD axion, that's right, yeah. It can, I mean, yeah, I can tell you later. I mean, we're using something like this for Wei and I and Pratik for the QCD axion for different reasons. So you can have a separation of scales. You can make, for example, the axion couple much more strongly to photons than to the QCD. And I think Andrea and others have done that to sort of talk about how you could see the QCD axion in some experiments that we're not expecting to see it. But yeah, no, for other reasons it will not be the QCD axion. Yeah, I guess also because we don't want the barrier to depend on the Higgs, yes. Because otherwise, if you start in the deep...
because in the original relaxon,
So we need a separate field. We need an axion-like particle. It's a separate field. And then from this Lagrangian, it's relatively easy to see that if these gauge fields are light, you can actually produce them very efficiently from this one coupling. And we've tried many other couplings and this with other types of fields, and this one, as far as we could discover, was the most efficient one because it satisfies the shift symmetry, so you can actually have it be relatively large without compromising. Oh, I guess I forgot to write the rest of the potential. Without making this too large, so it's a nice. It has a decent number of nice features. And to see it, you just sort of write the equation of motion for A, for the gauge field, in the presence of a background relaxant. So you just really treat phi as a classical classical source, and you include it in the equation of motion for A. And let me focus on the two transverse polarizations. I mean, because the Higgs will get a VAV, and it gives a mass to that. There's also a longitudinal one, but the longitudinal one turns out to not do anything very exciting, so I'll ignore it. And
The Higgs is charged under this gauge.
the Higgs is charged under this. Yeah, this is crucial. Yeah. So now, and I've also ignored the expansion of the universe because, well, for the simpler case, I won't need it. And it turns out that even for the cosmological evolution we'll have, it will not play a very big role as far as this particle production is concerned. And from here, one can already see why you can get very efficient particle production, which is, well, I can treat this thing here as some sort of effective frequency, right, that depends on momenta and on the values of phi dot. And, well, as one expects, the only thing that A is sensitive to is phi dot, because we know it's supposed to be shift symmetric. So if phi is a constant, it's just like a theta term for a U1 gauge field, so you know it shouldn't have any effect. And this can become negative if phi dot over F is bigger than the Higgs mass, than the gauge field mass, which is basically given by the VAV. So once this happens, you have a negative an imaginary frequency, and that just pointing to an instability in your system, which just means that now this gauge field, which had their own quantum fluctuations, these quantum fluctuations can just get exponentially enhanced, which means that you're just producing a lot of the quanta of these particles. And you do that at the expense of the energy that was stored in the relaxant, so that's why you slow it down, right? So, well, therefore, and this, just to be very clear, this depends both on momenta and on phi dot, and the sort of the largest growth rate that you get is for k's of order of phi dot over F. So this is the characteristic scale for everything. So all time scales and everything are given by this phi dot over F. So A starts to grow exponentially with phi dot over F, and eventually it grows so much that it takes an order 1 energy out of the relaxion, and it can sort of get trapped in one of these potentials, which don't necessarily need to have very large barrier height. So it responds to a light Higgs by creating a new friction instead of by changing its own potential. So that's the difference compared to what other people sort of other models for the relaxion. Oh yeah, it's the helices of A, yes. I guess polarization isn't because they're massive, but yeah, the same, yeah, the two circular polarizations. Okay, so now to there now will be a lot of relaxion things that we need to worry about, but as far as implementing this picture in the standard model, there's only one thing that we really need to worry about, and luckily it's relatively easy to go around it, which is in the standard model, I don't want to introduce new gauge fields that the Higgs is charged under, because that would make things too complicated, and well, we don't see other 100 GeV scale gauge bosons. So, but if I want to couple it to the weak scale, the electroweak bosons, I don't want it to couple to 2 photons, right? Because the 2 photons don't get a mass, and so they would start to be produced from the first moment, and it would just completely spoil my nice feature that the relaxion learns about the Higgs being light. And that's easy to do. So in the standard model, plus with the relaxion, I just have all the same things that I've added there, plus lambda b cosine, same thing, the epsilon lambda squared phi. But now the coupling to gauge bosons need to come with this, in this very specific form, because this is exactly the form that doesn't contain FF tilde of the photon. And this is a, well, somewhat special choice, but it has the nice feature that because those things are related to anomalies, it doesn't really run. So if you set it in the UV by some symmetry reason, you're safe in the IR. So if you're just trying to be very technically natural, you can do this. Or you can try to embed it into some sort of left-right symmetric model, which at very high scales, and then that's how it's generated. And typically running won't really spoil this relation, because these operators are protected, this alpha times BB tilde. So that's it. That's what we need to do to do it in the standard model. And yeah, I still have 10, 15 minutes maybe. Yeah. Oh, okay, good. Yeah, so now let's look at the. So this is the good part. This is sort of okay. It should work. FF doesn't have this nice instability, and I think my understanding it can get very large production, sort of because it can change the gauge coupling by large factors, and if it's doing that fast, you can also generate very large then it's not exactly through a tachyon, but it's through some sort of changing the kinetic term of the gauge field sort of very abruptly. But that coupling is not shift symmetry protected, and so then you can't really make it very strong, and so you run into, at least for relaxants, you run into problems. I know people have tried to use it for inflation purposes, sort of reheating, where I guess they care a little bit less about naturalness, and there it seems okay. Yeah, okay, and then let me just write, and yeah, I'll focus on the Z for now. It doesn't really, well, I guess I won't get to the smaller details that would really make the Z somewhat special, but it's the same equation, but let me just write it, including the expansion of the universe, just to show where it really matters. So this is what you get if you actually write down the equation of motion of A in an expanding background. This Hubble friction term is not really doing anything. If you go to conformal time, it completely goes away. But the issue is that now the condition for the modes that are being most efficiently produced through this tachyon is that K over A is of order phi dot over F, which means that sort of it changes over time. So if you're doing this too slowly, you start to exponentially produce one mode, and then the universe expands, and you start to exponentially produce a different mode. So you don't get to build up on this exponential. So you want this to happen relatively fast compared to the expansion. So that's the only sort of complication that arises from the expansion. But it turns out that for many reasons, we'll want it to happen fast compared to Hubble anyway, so this doesn't pose a big problem. And just that picture that I had here, right, for the barrier, now it's, in this case, it's more symmetric. It has many minima, but they're all they're all the same. But now, because you want these things, well, maybe I drew it not in the best way. You want them to be actual minima. So you need epsilon lambda squared to be, let's see, less than lambda b to the fourth over f prime. And f prime is the biggest one of the f's, which is the one that sets the range of the field. So maybe I'll go somewhere and I'll start putting all the constraints, because they quickly start to accumulate. Maybe I'll do it here, since I don't need to erase anything. So this is things that I need to keep in mind. So I'll need epsilon lambda squared less than lambda b to the fourth over f prime. This is one constraint, just otherwise no minima, if I don't satisfy this. The other one that I will impose, and that one, not everyone will agree with me, and it's just because I want to be extra safe, is that I don't want delta phi to have super Planckian field excursions. It's not clear that having super Planckian field excursions is bad, but given our lack of knowledge of quantum gravity and the fact that I'll be able to do it with by decreasing a little bit the maximum cutoff that I can achieve, I'll just use that because it's better to be safe. So that means, and if you remember delta phi, this is roughly given by lambda squared over epsilon. So that tells me that epsilon has to be bigger than lambda squared over m Planck. I also don't want phi, so this is,
Delta phi smaller than. No, here on the other side.
delta phi, yes, exactly, thanks. It's okay. No, and this is smaller too, right? Yes. And I also don't want the relaxant, so this is no super Planckian. So in principle, you can relax that. You gain a bit with the cutoff, but it's not enough for me to abandon this. I also don't want. No, let's see. This is not right. It's bigger, right? It's bigger. Yeah. That's what I thought. Yeah. Yeah, it's bigger, smaller. It's, yeah, 50-50. Yeah. I also don't want the relaxant to participate in the inflation sector because that might lead to complications. Although in principle it could be a nice thing, and people are trying to do there are a couple of papers already that are trying to make the relaxant or something that's associated with the relaxant play some role in inflation, but that complicates the analysis, and so I'll also step away from this, and so I'll want Hubble to be bigger than lambda squared m Planck. And that's just because the potential energy for phi during this whole field excursion, it changes by lambda to the fourth. So if the Hubble is given by lambda squared over m Planck, it means that it would also have changed by at least order 1. And it would have this funny coincidence of scales that the inflaton has similar energy scale to the relaxant. So I don't want that, so doesn't change inflation. Okay, and for now I think, and of course I want that the Higgs mass in adjacent minima to be separated by less than V. Otherwise it's incredibly lucky that I landed on V, right? So I need epsilon f prime to be less than V squared. So that's the difference in delta m squared between the adjacent minima. Okay, so with those things in mind, I can see how could the scanning have happened in the universe. And although you can do it even after inflation, I think the simplest and sort of more robust scenario for that we've found was to do it actually during inflation. So I'll focus on that due to the lack of time, and I'll be happy to talk about doing it after inflation over coffee or over lunch. So assume that phi dot sort of initial at the beginning of whenever you're treating inflation is bigger than lambda b squared. So you start off with significant kinetic energy. If you have that, you can show that phi dot, and also you need to assume the following. So that means that in the beginning you could scan, and then you need to see, can I continue scanning, or will Hubble friction by itself trap me on some random minima? So it turns out that as long as epsilon lambda squared over h, which would be some sort of phi dot bar. So let me say I just average out all of these cosines. I just make just use the slope here. This would be my slow roll velocity. So if this is bigger than the height of the barriers, it means that just the energy gain that I have from going from one maximum to the other maximum is enough to keep me rolling. And so this means that phi dot becomes roughly epsilon lambda squared over h plus a small perturbation, which is the perturbation given by this minima, which oscillates to 0. So the scanning velocity is still roughly given by this would-be slow roll. Of course, it's important that you're not really slow rolling, because if you're really slow rolling, you would immediately stop here. So you're sort of in this funny regime. But yeah, this is all just sort of classical equations one can solve and can do some perturbation with the potentials and show that. And so the scanning will happen. You start off with very large valves. Once you've canceled enough of the valves, you start to produce, right? So once m squared sort of becomes close to v squared, well, let me say differently, because this is just me engineering all the parameters. So in the beginning, so phi dot now is roughly constant throughout the whole evolution, right? And so I can say that phi dot over f is going to be much smaller than lambda, the cutoff, which is the initial valve. So in the beginning, I can't really produce the particles because they're too heavy. They can't be exponentially produced. So the scanning continues until M Higgs, sort of Higgs becomes of order phi dot over F, this phi dot bar. Once this happens, I start to produce particles, and I have a chance of falling in one of those minima. Okay. Oh, it's just this average. Yeah. It's just for the lack of a better name. And then I have to see if I can fall in one of those minima. Unfortunately, I guess I'm short on time, so let me just. I'm good. Okay. Oh, okay. Yeah, we don't even know if the restaurant is open, so I guess we can just talk physics. Sorry? So the barrier heights, sort of the difference in energy between the barrier heights is typically sufficiently large that tunneling is suppressed within timescales of the universe. So if you waited very long, you would get tunneling. And so I know a lot of people, a lot of my colleagues at Stanford are not happy because they think that, well, the universe maybe exists for very long. But in principle, if you just assume that, well, it happened during inflation, and then the amount of time that has passed until now, the tunneling is small. It's okay. Yeah. But I mean, even just tunneling to more than once. I think maybe you can tunnel once, but the adjacent minima have similar VAVs. But so even because these barrier heights are bigger than the ones in the original Relaxion, for example, and there they show that even those ones, which are pretty small because they were using lambda QCD, it was already very long time scales for tunneling. So here it's even safer. And this F prime is pretty large, so you need to tunnel very far. But yeah, in principle, it's a worry, and depending. And partially I'm not worrying because I'm assuming I can set up some initial conditions for inflation, but I don't really know how those started. So yeah, but what happens once you have start producing these particles? You start losing energy of the phi, but once you start producing a lot of this phi, I've just said that, well, I want my parameters to be such that this is V, sort of 100 GeV, right? So I start producing all these gauge bosons with 100 GeV energy, and very large numbers of them. And they quickly start interacting with each other, and they form a plasma, right? So they take decent chunk of the energy, and they form, you get a plasma of standard model stuff, a standard model plasma, with temperature, sort of order, whatever was my phi dot, in the, I don't know, when particle production started, which is this epsilon lambda squared over, I guess it's square root of that Hubble, because those are the energy densities in the stuff I'm producing. And then, because you have this plasma, two things happen. One is good, which is, well, T is bigger than V, right? Because you're taking the kinetic energy in the relaxation was larger than V, because when I divided by F, which is a number larger than the cutoff, I get 100 GeV. So this means that electroweak symmetry is restored. So MZ, MW all go to 0. Which is good because it allows me to continue to lose energy, right? Because otherwise I could only lose energy until phi dot became smaller, phi dot over F no longer satisfied that it's bigger than the mass of the gauge bosons. So this part is good. The not so good part is that, well, plasma effects actually are important. And they slow down the particle production. And this is just an analogous effect from sort of screening effects that you know exist in plasma. So you know that gauge fields get Debye masses, and for a long time we were worried, well, maybe Debye masses are just the same as normal masses, but turns out they're not quite. But they're still not great. And the way to incorporate this sort of plasma effects is you can write down the dispersion relation for the gauge field. Before it used to be just minus omega squared, k squared plus, there was some m squared and minus plus dot k over f. It used to be equal 0 for when it was sort of at 0 temperature. But now it has some finite temperature dependence, which is just some polarization tensor when you're traveling through a plasma. And this is in the regime that we're interested in, which is omega is imaginary, right? We want to find sort of unstable solutions. And it turns out also that the regime where we'll find interesting solutions is when this new imaginary frequency now is much smaller than the momenta associated with those modes, which is not what happened in the 0 temperature case, in which those two were the same. And this is much smaller than the temperature. So this is the regime. In this case, pi t is roughly m squared dBi, absolute value of omega over k, and I think it has some 4 pi or some pi here, where m dBi is gt, so it doesn't even have a loop factor or anything. It's pretty big. And if you plug that in, but the nice thing, the reason why it's nice is that, and then there are higher terms plus order sort of omega over k terms. It's really m dBi squared times some series of this omega over k terms. But because we're interested in this regime, we can truncate to the first term. And the nice thing is that there's no sort of constant piece, right? The 0 piece would really look like a mass, and it would completely shut down the effect. But here, it doesn't happen, so that's a good thing. And that's partially why you need to do it with U1 gauge fields. For non-abelian gauge fields, there is a 0 mass, which is this magnetic mass, which I don't fully understand, but that would completely shut down this effect. And so in this case, omega is roughly given by phi dot over f, now cubed over the dBi mass squared. So we see that this is the same as before, times something that is definitely significantly smaller than 1. So it definitely slows down significantly your process. And so you need to make sure that, well, now, unlikely that in the first part of the process where you've just thermalized this, you actually got trapped. So you need to see that, after I have this slower growth rate, do I still get to stop in the minima where the Higgs mass is V, or maybe it just takes me so long to stop that I completely lost memory of when I started. So you need to see, is it efficient? And so you need to see if delta of the Higgs mass squared, which is sort of m squared Higgs, when you trap minus when particle production start, this should be less than v squared, because you wanted to have a memory of where it started, up to corrections of the size of v. And well, this is in principle very easy to estimate. Delta m squared is just epsilon times delta phi. So you just need to estimate how far phi traveled once you start producing these things. It turns out that it spends most of the time trying to lose the last bit of energy, well, because the rate is going down and down. So you can estimate that by just using epsilon phi dot at sort of the very end, and delta t, which is the typical time that takes you to lose an order 1 of energy at this end. And so this is epsilon phi dot, and then omega minus 1 when sort of at the end. And at the end, you want phi dot to be smaller than the barrier height. So I'm just going to replace phi dots by lambda b squared. Okay, so that if I plug all of that in, I get epsilon. Let me see, I get. Let me copy it. It's easier. epsilon t squared f cubed over lambda b to the fourth. And I need this to be smaller than v squared. So that gives me an upper bound on epsilon. And I had this lower bound here from my super Planckian field excursions. And that lets me actually put, that's how we get a relatively strong constraint on our, the maximum cutoff that you can have. So if I combine everything, I get that, well, I have lambda squared over m Planck. It's less than epsilon, which is less than v squared lambda b to the fourth. So some combination, but with many of these big parameters. And I can sort of massage this expression a little bit, and I end up getting the following bounds that lambda squared over m Planck, which is the size, and I can sort of massage this side a little bit and use some of the other inequalities to write this as v to the fifth over lambda squared times something that is h over epsilon to the fourth. No, squared, sorry, squared. And h over epsilon squared is exactly the number of e-foldings you need to scan. This is sort of parametrically, so I can replace this by what is the minimum number of e-foldings that I need to scan. So now at least I know that, well, I can increase my cutoff a little bit by maybe making my inflation sector a little bit worse. It only brings you so far. It doesn't actually get you. Delta n e has its own bounds. But with this, and maybe I'll end here so we can have lunch. If I want delta n e sort of roughly 100, so sort of parametrically the size that we usually have inflation models, I can raise my cutoff to be about 10 to the 5 GeV. So it's a solution to the little hierarchy problem. It doesn't really have any new particles at the TeV scale, at least no new particles that talk strongly to the standard model. You need something that creates this barrier here, but because this barrier doesn't really need to talk to the Higgs or anything, it only talks to this very weakly coupled Relaxion. I don't think we would probably ever see it. But we know that we would need to sort of solve the real hierarchy problem at 10 to the 5 GeV, so at least tells us that maybe new physics, even if this very pessimistic scenario where there's no new physics at TeV scale happens, new physics couldn't be that far. I think that, yeah. No, there is. So in this, yeah. So at first I thought that, but actually in this construction at least there is a bound. Yeah. Even this here is somewhat specific to my construction, but delta NE had to be less than lambda squared over V squared. So I think if I crank it all up, but I still keep the super Planckian field excursions, I only push it to 10 to the 6, but I push the number of e-foldings by a lot. So it's like, it doesn't seem like a good trade-off. I'd rather, and it's still 10 to the 6 GeV is not that far. Yeah. Oh, yeah. Let me see, I derived it yesterday. It's coming from this. You need phi dot over f during the scanning to be v, right? And this is epsilon lambda squared over Hubble over f needs to be v. So now I can do, so this implies h over epsilon is lambda squared v and f. Now f can be has to be bigger than lambda, and now I square it and I get that bound. Yeah, that's how you get it. It's specific to this construction. Yeah. So if you did it, but unfortunately, from all the things we tried, this was the one that allowed you to push the cutoff higher. But maybe it's just lack of. I hope it's just lack of imagination, or just that we got too tired. I mean, we tried this for a long time. Okay, and yeah, that was all I prepared to say.
Okay. Questions?
Yeah. Yeah, so
They're using your mechanism, but how do they avoid this delta hanging down?
yeah, they're using.
They end up finding the
Yeah, I haven't fully understood their mechanism. So they have this thing that their barrier also depends on the Higgs valve, and but then it sounds like some funny coincidence. So it has too many knobs. I haven't quite figured out how they are doing it so efficiently. Oh, sorry. I sort of know. They're not producing something that has a thermal mass. So they're friction, because they're producing this, which I still am a little confused, because they produce this dark photon which has a small kinetic mixing, such that somehow later they can transfer the energy from the dark photon to the standard model, but they claim they never get this Debye mass type slowdown. So that definitely helps them quite a bit. I haven't checked to see if that's just if that's the only thing that's changing there. Yeah, I don't know.
Okay. Can you get away without the slope term and the potential? You start with enough kinetic energy so that
Yeah, so the problem there, so we well, you always have the slope, but maybe the slope doesn't really help you, because you need to put in a small shift. I mean, you need to put in, unless you somehow have a very smart. Yeah. So yeah, but maybe you can play some game where the slope is so small that it doesn't really matter. But there will always be some slope. Yeah, it would be great, because then. Yeah. So it would be great, because then it wouldn't. It would deal more nicely with the CC, right? If all of them were at the same level, but that's okay. Yeah. It has double interaction. Oh, that's a good point. Yeah, because a lot of times we are relatively light. Yeah, I should check. That's a good point. Yeah, I mean, yeah, it's a good. Yeah, I haven't checked. Should ask Brian. I guess he'll still be there when I go back.
So I don't see any more questions. So let's thank Gustavo again.